Hello and welcome back. So we recently learned about these nice looking Perceptron models, which I have on my screen right here. Hopefully all of you can see my screen. And now we're going to learn how to program one of these from scratch and run it on the Iris dataset that we learned about, or that we were talking about in that recording. So as always, we're going to import the following three packages pretty much throughout the entire semester. So matplotlib.pyplot.plt, import numpy as np, import pandas as pd. And then we're going to import two other packages that I want to use. So I'm going to import Seaborn just for the styling in the plots, and that package as SNS. And then also this new package that I found recently that's good for, that's really easy to use when plotting decision boundaries with machine learning models. So MLX10. So MLX10. And then from that module, I'm looking at plotting, and I'm going to import the function called plot decision. And then I'm going to set my theme for my plots to the Seaborn theme. Okay. What did I do wrong? Oh, from. Why did I do that? So from this module, I want to import that function. All right. Okay. So now all of you should have the Iris dataset in your current working directory. So if I look at my directory right now, this is where I'm at. And then inside of here, I have this Iris dataset right there. So I have direct access to it. So I can read that in with the pandas read CSV function. And that's what I'm going to do first. So I'm going to say df, which is a common way of naming data frames, is equal to pandas pd dot read CSV. And then I need to give it the name of the file. And the name of the file is iris underscore dataset.csv. Okay. So far, so good. This should be pretty familiar. Next up, I want to grab all of the, well, if I look at the data set, I have sepal length, sepal width, petal length, petal width, and the species in the last column. And the first 100 rows of this data frame consists of the Setosa flowers and the versicolor flowers. So that's what we want to focus on. The Setosa and versicolor, we want to classify those species based off of their sepal length and sepal width. Okay, so in order to get that information out of the data frame, there's a little bit of data manipulation I need to do. In particular, I'm going to say y, which are like the y values from the slides in the previous recording. So y is equal to df.iloc 0 to 100. So iloc, if you remember, integer location on the rows. So I'm getting the first 100 rows, non-inclusive. And then that's the data frame itself. And I'm going to grab the species, which will grab the first 50 species. And then I'm going to use the .values attribute to just get those attributes. So this is really, if I run this and I look at it, it's just an array of all of those rows and columns. I mean, all of those rows on that species column from 0 to 100. So that's all that's doing there. But these are strings. I need them to be numerical values. So we need to convert these strings into ones and negative ones so that we can compare them with the sign activation function that we're going to choose as our activation function, again, shown here. So in order to do that, we can say, we can use this mp where method. So mp.where y is equal to Setosa. We want it to have a label of, I'll say -1. Otherwise, it should have a label of 1. Okay. So this is saying where in this NumPy array, is it Setosa? Wherever that is true, it's going to return a -1. And if I want to stay consistent with all the strings in there, you don't have to, but I like being consistent with these things. So wherever it says Satosa, we're going to have a -1 put in place, and then everywhere else it'll be a 1. That's if I run that cell, and now I look at Y again. We see we have -1s for all the Satosas and 1s for all the Versailles color flowers. So this is just a little bit of pre-processing to get my labels. And then for my X values, the features, I want to be the first 100 rows of sepal length and sepal width. Okay, so to do that, I can say df, making sure that I spell it exactly the same, underscore. Okay, so sepal length in the first entry of this list, and this next one will be sepal width. That. Now I don't want all 150 rows. I just want 0 through 100, so I can do .iloc up to 100 non-inclusive. So you don't have to put the 0 there if you just want to go slice up to 100. Again, non-inclusive. And then I'm just going to grab those values like that. All right, so now there's my Y. What does my X look like? So we have features and then corresponding label. Feature, label. Feature, label. All right, so it looks like we have some good data to work with now. So now that we have our X and Y data, we might want to move on to the actual perceptron itself, right? This perceptron is a very general idea. Well, the perceptron is a specific instance of the single neuron model, right? Just with the choice of this activation function, the sign activation function. So because we might use this model over, or we might encounter this model next class, for example, I'm going to store all of this data in a class, right? So a Python class. So last time we learned that Python classes are containers that contain data and functions, right? This is precisely a good place to use this. We have data, which is the weights, and then we have a function. So we can store the data and the function in a Python class. Okay, so I'm going to go ahead and write a class to do so. So class, not always, but I typically like to label my class objects with a capital letter. So I'll just call this Perceptron like that, and it is an object. All right, so now we're inside of my class that I'm defining. And as we learned in a previous lecture, we need this double underscore init method to initialize the sum of the data of this object when we make an instance of it. So I'll say def double underscore init double underscore. Every function has to reference self, right? The given instance of the object. And I will say, what did I use earlier? I used something like eta. Maybe I'll use eta. So eta is equal to 0.5. That eta is going to correspond in the update rules to this 1/2 right here. So we can change that if we want to. I'm going to set it by default equal to 0.5. Okay. And then let's say epochs. So how many epochs are we going to run through? If we look through the algorithm, an epoch is an application of part 2 here, where for each of the I 1 through n, if that's the number of data that we have, update the weights and bias. So we feed forward, get a value, update, update. So maybe I'll set this by default equal to 50. I don't know. Okay, so then I have to assign these attributes to the given instance self. So self.data is equal to data, and then self.epochs equal to epochs. Right, so that's just setting this coefficient of the update that we're going to use, or we're going to implement, and containing the number of epochs that are going to run over when we decide to train this thing. All right, so speaking of training, let's write a train method now. Train, every method has to reference self again, but now we're going to pass in X and Y. So these will be, as you saw earlier, we have features, and for each of those features, we have a corresponding label. And we're going to use that to train the weights according to this perceptron algorithm. Okay. All right. So when we do this, we don't have any weights currently, right? We haven't initialized our weights. So what we can do inside of train is at the instance that we call the train method on an object, we can set the weights at that call. So I'm going to say self.w. I'll use an underscore because it's similar to what scikit-learn does, and we'll learn about that package in a few weeks. But for now, just self.w underscore, those are the weights. empty.random.rand. This is one way of doing it. 1 plus x.shape1. So what is x.shape1? So if this is my x out here, which is global currently and not contained in this block, so x.shape, that returns the dimensions, right, of that matrix. And the one entry are how many features there are. So what's going on here, we're making weights to be equal to 2 plus, so it'll be a random three-dimensional column vector. So this is similar to using this, this bar notation. So this right here is doing precisely this. It's making a random vector with 3 entries in it, which is what we need. All right. Now, as we're training, it would be nice to keep track of the errors that we are incurring after each epoch. So I'm going to go ahead and assign a data attribute to Perceptron called errors. This will be a list that will contain the misclassification error that we get. All right, so now we need to run through the epochs and apply this update rule. Okay. Again, there's 2 different ways to do this. We can choose which one we're going to do. I don't know which one I'm going to do yet. We'll see. For underscore in range self.epochs. Right, so this is just a loop, right? And it's a convention in Python when you're not using a variable while looping to use the underscore. So it's like a dummy variable just in place. But again, this is just running through 0 through the number of epochs minus 1. Okay. Now we're in this for loop and we're going to have to do things, right? What do we do? Well, for each epoch, we want to count the number of errors that we get. So maybe, or then so we can do something like errors equals to 0 first. And now that we have that, now we can scroll through each of the data points in this script D. Right, so we can do, say, for xi, comma, y, or maybe I'll call it target, be a little bit more specific, and zip x, y, like that. So this is pairing up each of the feature vectors with the corresponding label. So for example, if I did like xi, comma, target, and zip of this xy, xi, comma, target, and maybe I should just do this. P, like that. Oh, live coding is always hard. Oh, I had a silly typo right there. P4, P and zip, there. So zip just collects the data into tuples. And we can unpack those tuples with this here. Okay, so xi will be this, and then target will be this. And the next time it'd be xi is that, target's that, so forth and so on. So we're just looping through all of the data, just like the algorithm tells us to do. Okay, next up. So we need to maybe break this up into pieces. So we need to calculate our output, right? So we need to predict the y hat. So maybe what I can do is I can write something like update equals self.data, which is this numerical value here, right? That 1/2. So I'm going to call this thing here like my update. So self.data times, now I haven't defined this method yet called self.predict xi. So I'm going to have to, after this train method, I'm going to have to make a predict method. Okay. Minus. All right, so this is our y hat right here. This is our y right there. So this little business, the 1/2 times the difference of the y's, that's what I'm calling update. Okay. And then I can say self.w underscore, because that's what I named the weights up there. So remember, the way that we've defined our weights is a 3-dimensional column vector, so it looks like this, right? So we want to only update the 0 entry and the 1 entry. So everything except for the -1 entry with this rule here, the weight update rule. So we can do that by saying that weight vector all the way up to the -1 entry. And again, we're not including that v there. And then we'll say minus equals update times xi, right? So that's precisely right here. This is update xi minus equals, that's exactly what's happening right there. And we're only accessing these first values in the weight. And then we need to update the bias term in that weight bar vector. So b, which is the last term, so self.w underscore -1 like that without the semicolon, that accesses the very last term. And this is just minus equals update. Because if we look at the Perceptron update rule in that case there is no x multiplying it at all. Okay. All right, and then maybe we can add to our errors integer value of update not equal to 0, right? So notice that if this thing here is equal to 0, then we got it. If this is equal to 0, we got it. Like we predicted the correct thing. But if it's not equal, then we need to add the errors that we got it wrong. So it's going to just convert that to an int. And then after that for loop, we can do self dot errors, which is this errors attribute here, dot append the errors variable. Okay. Okay. And we don't really need to return anything. So if anything, I can just say return self maybe. Just return the object that we're currently working with. So I need, what do I need? I need an input value maybe, and maybe like a predict value, method, I'm sorry. So def dot net input is what I think I was using before. So reference self and x. And this is just going to return a dot product. So np dot x with self dot w underscore. Again, when you are dealing with this bar notation here, the weights are everything except for the last term that are multiplying with x. So we're going to slice up to the -1 term like that. So x dot that, okay. And then plus self dot w underscore, and then the last term is the bias, right? So, oh, why did I call it new? I think net. And then next up, so this is just the weighted sum. That's it. So net, weight, whatever. And next up, we have our predict method, which is being used here to predict the label. So self, and then x, and then return. We can use that where method from NumPy again, where self.net input x. So here I'm calling this net input, so the weighted sum. So this is the weighted sum right there. And we're using this where functionality. Where this is greater than or equal to 0, we're going to return a 1, and then otherwise return a -1. So that's the predict value there. So if we're given x, maybe I should have used a lowercase x, but I'm trying to indicate that that is a vector. But yeah, it's just a single x. It's that dot with that there. So, but you can also, this could work on the whole matrix itself, and that's where this would come out. But yeah, actually, no, this is, I got that wrong. It actually works out better as a matrix. I just realized that because this is going to return a matrix, and this is going to return all the values. This will return a column vector that gives, for all the data that you input, these are the predictions. And I think that's it. So here it's predicting on a single value, but here it can predict on an entire matrix of values. I think that's all we need to contain the perceptron. All right. So now that we have that, we can make a perceptron. Let's go ahead and do it. Like I'll call it that maybe is equal to perceptron like that. And because I ran this stuff earlier, I'm going to have to change the number of epochs, I think, for these measurements. So I'll say epochs equals to like 1,000 or something. And by the way, you can always do the underscores to indicate commas. So this is 1,000 epochs. And then once I've made that object, I can train it. So I can do set dot, call this train method right here, like that. And then I already have my x and y defined up here. I just have to pass those into that method. Okay, so just pass in x comma y. This is annoying me right there. So this is instantiating the perceptron class, and I'm changing the epochs to be 1,000. And then I'm calling the train method on that given instance. If I did everything correctly, there shouldn't be any errors. All right, no errors. Okay, it's been trained. So now that it's been trained, we can visualize the decision boundary using that function that we imported earlier, plot decision regions. So we can do, just call that function. That's the name of the function that we imported up here. Okay, and then we just have to pass that in the x values, the y values, and the classifier that we were working with is our custom classifier called percept. Okay, and I'm going to make the figure a little bit bigger by calling plt.figure big size equals to 10 by 8, like that. And then what else did I want to do? plt.title, maybe my first perceptron, like that. Maybe that. And then plt.xlabel. This was, what was it? What did we pick up here? It was sepal length and sepal width. So sepal length. Sepal lengths, and this is in centimeters. And then for the Y label, this was, I accidentally ran that. Y label is sepal width in centimeters. And then we just need to show it, plt.show. There it goes. And it looks pretty good. That's a good, nice split of that data, right? Now, just so you know, it's because of how many times we ran through this, right? Which is, we can look at and actually visualize how long it took to get this boundary, because when we called the train method on our instance, notice that in here, we made an errors attribute. So we can plot those errors, right? We can like call that attribute and plot it. So let's look at what the errors look like over time. So POT.figure big size equals to 10 by 8. POT.plot. So I'm gonna say, because we need to start at 1, so at range 1 to the length of percept dot errors. Yeah, that's what I called it. I kind of want to stay consistent here, but this will work. No, I'm going to stay consistent. I want an underscore right there. So I'm going back up to my cell and I'm putting underscore there. And then here, I'm putting an underscore there. Because, yeah, I didn't like the way that looked. So I have to run that cell again. I have to train it again and instantiate it again. Make sure that the decision boundary looks good. So it does. Okay. So there. +1. So that's my x. Those are my x values, the integer values 1 through the length of this +1. And then for the y values, I'm just going to look at what's contained in there. So percept.errors underscore like that. And then so that's my x, that's my y, and then I want a marker too. So marker equal O. That's so it'll mark those discrete values, give it a label, error plot, like that maybe, comma, and then that's it. So, and then POT.x label, these are the iterations. POT.y label, these are the error values of the misclassifications. Because again, we were converting it to an int whenever we didn't get it right up there. So this would be the number of misclassifications in that array, or that list. Show your legend, and then show your figure. So that's what, that's how long it took us to get an error of basically it's 0, right? So for all of this time, that many epochs, which that's the number of iterations, right? It took that many epochs to start dropping down. So over 600 epochs for this data, right? So again, I'm just plotting integers 1 through the length of this +1, then plotting the errors that have been contained in the percept.errors attribute. And again, we were populating the entries of this after running through an entire epoch. So each time we ran through an epoch, we populated all the times where we didn't get it right. So it was counting how many times, and it took a while to drop off. Now you can, if you want, like, what are so petal length, so sepal length, sepal width. So maybe you could try like putting in like petal length in here. So like maybe if you wanted to, length like that. You have to run that again. So I have new x values. I have to instantiate and train again. And then I'll change my x label or my y label here to be that. So that's sepal length versus petal length. And actually, if we look at I'm curious now, look at the errors. Yeah, it dropped immediately. Yeah, it found that decision boundary quickly because look at how separated these data points are. It didn't take very long at all. Like I could have done this. It looks like maybe I can just try it again with 10 epochs. And it's basically the same thing.
Professor?
Yeah, yes.
I'm sorry, like at the very beginning, when I ran this from mlxt10.plotting,
Yes.
it still shows me an error that it cannot import the plot regions.
Okay. Let me actually, I think I'm done with this lecture and I can answer your questions now. So let me go ahead and stop the video. This has been a recording on programming in the perceptron from scratch. So I'm going to stop it, and that'll be it.